Hello everybody and welcome back to this crazy section that we got to. Alright, so we ended up saying that we have our inertia tensor, which is with I and J, and I want to say that this inertia vector will then be a matrix that is a 3 by 3 matrix. So let's expand this matrix. Let me start writing it down. I actually found this part pretty beautiful, and I think you'd see why soon enough. Okay, so if you remember, our I is equals to this part right here. So I'm going to bring it down so we can work on it very quickly. Alright, so first thing first, I'm going to have the summation of the masses still present. I'm not going to solve it. The only thing I'm going to do is use my I and J. So for position 1, 1, our I will be 1, J will be 1, so our chromatic delta is going to be equals to 1. So it's going to be the summation, I'm going to write it a little quickly, k of x alpha k squared. So we have to solve this. Well, that means that we're going to get x alpha 1 squared plus x alpha 2 squared plus x alpha 3 squared minus the second part right here. We said that I and j are the same, so we have x alpha 1 times x alpha 1, or we can simply write it as x alpha 1 squared. And as you can see, these two cancel each other out. So we ended up having what? Well, we end up having, let me take this, cancel it. We said take this as well, cancel it. This is our product. Oops, zoom back. There we go. Now, for the second part, again, summation of the masses. And then, in this case, our position is 1, 2, right? So our chromatic delta for 1, 2 is going to give us 0. So this first, part will be equals to 0. So the only part that we're interested in is the second part with negative x alpha 1 x alpha 2. Or we can rewrite this as taking the negative out in front, and this is our equation. Now, why did we change the I and not the J? Doesn't matter. You want to change the I, you want to change the J? Well, let's imagine instead of changing the I, you get the J. So you have x alpha, so we're going to say 2 x alpha j. This is the same thing as x alpha 1 x alpha 2. Oh, I forgot. Here's 1. These two are the same thing. So that means that our matrix I j is equals to our matrix j I. Or we can say that our matrix is equals to the same matrix transpose. Anyway, let's keep going. So we're doing it. So we're gonna get x alpha 1 x alpha 2. Now again, in this third position, our I and j will be equals to 1 and 3. Therefore, our first part is equals to 0 again. So we can ignore it. It means that we're going to have the second part only, so we can put a negative in front. Summation alpha and alpha, and then x alpha 1 x alpha 3. Second part, second line. So we're gonna have summation of the masses alpha. Now again, the first part, we're gonna have our I and j to be equals to what? It's gonna be equals to 2 and 1. So the first part equals to 0, so only the second part of our parentheses will give us something. So we're gonna have a negative in front, x alpha 2, x alpha 1. Write this a little better so you understand these are subscripts. Now, for this center one, I and j is going to be equal to 2, 2. So this convergent delta is equal to 1. So we finally get something from the first one. So we're going to get the summation of our masses and alpha, and then we're going to get x alpha 1 squared plus x alpha 2 squared plus x alpha 3 squared, right there, okay, minus, then our, is it I and j is going to be equal to 2 and 2, so we're going to provide it as x alpha 2 squared, so these two cancel out, and that means that we get, oops, we get this product right here. Move this a little more to the right. Okay, now again, in this second row, third column, our I and j will be equals to 2 and 3. So our chromatic delta will be equals to 0. So again, we're going to have a negative in front, alpha, sorry, summation of m alpha, and then our I and j is going to be equals to 2 and 3, so x alpha 2, x alpha 3. Okay, then third row, first column, our I and j are going to be equals to 3 and 1. So our delta again is going to be equals to 0. So we're going to have a negative in front, summation of m alpha x, we said alpha 3 x alpha 1. Then again here, again negative because our I and j is going to be equals to 3 and 2. So our delta is going to equal to 0. Summation of m alpha, the alphas, of x alpha 3 x alpha 2. And then here I and j is going to be equals to 3, 3. So our delta finally gives us 1. So we have to take into consideration that first part. So we're going to have the summation of m alpha, of the alphas, of x alpha 1 squared plus x alpha 2 squared plus x alpha 3 squared minus x alpha 3 squared, because I and j are going to be equal to 3. So we cancel out this plus 2. So we just erase this 2. And this is our complete matrix. It's a pretty cool matrix, actually. As we said, already transpose is going to be the same, so it doesn't matter if you write I and j first. One more thing you have to take into consideration is if the object has a continuous mass of density rho in terms of r, then our I of ij, on the other side, ij is going to be equal to the integral, of course, going to start with the summation, we're going to have the integral of the mass times the chromatic delta ij summation of x alpha k and the k minus x I x j k dv. Okay, yes. This is pretty straightforward. I ignore the alpha because again we're not integrating the alpha. Sorry, he actually wrote the alpha. I don't have to. Because we don't have the summations on the alpha anymore because we're talking about the integral. That means we're gonna have xk and xi and xj. Now of course dv is actually dx, or better, dv is actually equals to dx1, dx2, dx3. Because the volume is going to be in all three directions. Or, we can write it better, is equals to dx, dy, dz. Anyway, before we go ahead, I want to take, oh, you know what? Yes, let's do it anyway. We can take this matrix that we have right here, copy, and bring it down over here. Oops. It doesn't want to copy, I guess. Okay, paste. Instead of running this weird thing right here, we can do something else. So if we think about it, R of alpha is equals to R alpha, sorry, X of alpha 1, comma, X of alpha 2, comma, X of alpha 3. So R of alpha squared is equals to X of alpha 1 squared, comma, X of alpha 2, subscript again, 2 squared, comma, X of alpha 3 squared. So we see that we have two things right here. The only thing that is missing is the x alpha 1 squared. So we can simply write this as r of alpha squared minus x of alpha 1 squared. And we can do the same thing again for the second one right here. So we're going to have r of alpha squared minus x alpha 2 squared, no, squared inside, and here again, r alpha squared minus x alpha 3 squared inside here. Now, the book probably understood that the notation was pretty dumb, the way he used it, and so instead of using x with the comma 1, he used x for the first one, so we just like this, and then y, and then z. I don't know why the book decided to do it at the end instead of using it all along. I think it would have been just easier and just faster to write, but better late than never. So this is our new matrix. But a little more simpler, I would say. Let me know if you have any question. This was part 2 of chapter 11.3.